Today we're going to talk about different pre-compliance measurements, including some radiated emissions testing, conducted emissions, and immunity, and how we can use different test setups to visualize, validate, and to debug different compliance test challenges. Overall, we're going to talk about how you can improve your design process to better prepare yourself for final compliance testing. Let's get started. So here's our agenda for the next 45 minutes or so. We're going to do a quick introduction about pre-compliance measurements and then how they can inform the design process. We're going to talk about basic visualization in radiated, conducted emissions. We're going to talk about probes. In validation testing, we're going to look at different setups you can use for radiated, conducted, immunity testings, and some different techniques we can use. We'll also be talking about debugging, how you can use things like time correlation and real-time capture to improve how you debug pre-compliance issues and emissions issues. And then at the end, we'll talk about some solutions and accessories that we talked about today and further resources that you can use to improve your EMI measurements. Pre-compliance measurements really encompasses all the emissions testing we do during our design process to help us build confidence and better prepare for final compliance testing. The goal here is to save time and money by not having to make late cycle design changes to avoid compliance issues. This is best done through iterative testing throughout different phases of the design. Commonly, we'd use a spectrum analyzer here with some EMI features to help kind of best prepare us and make those pre-compliance measurements as much like a true compliance measurement as possible given the variety of setups, probes, and capabilities we have in our design lab. So let's take a look at EMI measurements in the context of an engineering design process. Here, let's think about a basic iterative development process where engineers implement new features, test, and then resolve issues. With EMI pre-compliance measurements, we can use basic visualization, just like you'd use a scope on your bench when you're building and designing out these new features. As you can move into a test phase, you can use EMI validation tests with a little more setup to help you make sure that emissions, whether they're radiated or conducted or immunity, aren't causing issues for you as you integrate your new features with your existing system. And then as you work to resolve issues and find problems, you can go into a debug mode where you're using EMI pre-compliance measurements to debug issues like radiated and conducted emissions that might be causing you problems later in your design cycle as you move towards final compliance testing. There we'll use features like time correlation and other important real-time debugging tools to get the most out of your pre-compliance measurements. So now let's take a look at each step in this process and how we can use different setups and different tests to really maximize the value of pre-compliance in each phase in your development process. So first, let's go ahead and look at visualization. So in basic visualization, we're looking at, again, trying to visualize emissions issues as we're implementing new features. The goal here is really to identify problems as soon as they enter into a design. We can solve problems in real time, make sure we're not causing any issues that we're unaware of. Typically, we'd use a swept spectrum analyzer in this kind of mode, and the goal really from an EMI pre-compliance standpoint is a simplified setup. This is on your bench as you're trying to implement new features. You don't want a complicated setup room you have to go into. So we're going to talk about different setups that are really very easy to use and made for your benchtop, for your desk. We're going to talk about both radiated and conducted emissions and how we can use simple probes to make these test measurements at a visualization standpoint. Let's go ahead and look at the first setup. Our first test in basic visualization is looking for radiated emissions. Here we typically use a near-field probe, like one of these loop-type probes you see in the pictures. We can sweep wide frequencies. This helps us avoid missing potential issues that might be outside of our span. Typically we use features like preamplifiers to give us the best view. One of the keys is to make sure we position our probe near edges of the enclosures, gaps, connections, things that might act as antennas for our radiated emissions. Let's go ahead and take a look at a quick video on this. Near-field probes are great for use on your bench because they're all about position and orientation. You can see these radiated emissions up close on your spectrum analyzer. In a swept mode, here you can see them about once a second based on your hand position. Another type of basic visualization is one used for conducted emissions. You can use an RF current probe like these on your bench top around one of the power lines. This allows you to monitor emissions being put back into the power line that might eventually become conducted or radiated emissions problems later in a compliance test. Here with our spectrum analyzer, we typically do things like limit our span to the common conducted frequencies, use preamplifiers. We might even use real time for more in-depth analysis of the kind of issues we might be facing. Let's take a look at a video on conducted emissions basic visualization. On our bench, we can use a power line divider like this one to separate the hot and neutral, allow us to put our RF probe around it. Here we're connecting to a little LED light bulb. Looking at the spectrum analyzer, in real-time mode we can see DC to 150 kilohertz and really capture all those low frequency peaks from the device under test. In this case, see what the LED light bulbs are putting back into the power line. So those were some basic visualization kind of setups and tools we can use on the bench. Now let's look in more detail at validation testing. So as you go to the next step in your iterative design process and you're testing other features and capabilities as you're integrating your electronic product, you can do validation testing on pre-compliance as well. Here we start to use more complete setups that get a little more complicated than just basic visualization, but allow us to make measurements that are also more closely related to your final compliance measurements. Also makes it possible to monitor how things are changing and improving over time in your design. We're looking at validating results versus our earlier versions, or starting to look at established limit lines that might become relevant in a full compliance test. So the goal here is really to just track our performance, build confidence, and monitor changes in our system so that we're aware of any emissions challenges that might need to be debugged or might come up to a final compliance test. We also at this stage start to use a spectrum analyzer with some dedicated EMI functions. This makes it possible to look at quasi-peak or CISPR average detectors, look at your bandwidths, RBW settings that are more commonly used in EMI. So all that's important as we get into validation testing. So here we're going to look at some different setups for radiated, conducted, and immunity testing to give us a full set of emissions testing we can do in a validation setup. Let's go ahead and look at the first type of validation setup. Our first validation test setup is really looking at radiated emissions. Here we're going to use a TEM cell, or a transverse electromagnetic cell. This TEM cell, as you see in the picture, operates really as a strip line device. What this means is, by placing our device in the center of it here, this open TEM cell, we can get really more repeatable radiated emissions information by setting up and connecting this to our spectrum analyzer. So this is a great sort of middle ground between a full chamber and just a near field probe like we were doing before. It gives us a repeatability. Let's see how we connect that. Let's take a look at a quick video on setting up our TEM cell. So this is our basic TEM cell configuration. On one end, we've connected the spectrum analyzer through a DC block. It's our little DC block there on the end on the left. Through the TEM cell with the product under test in the middle, below the septum. And on the right-hand side, our 50 ohm load. So this is the standard configuration. In an open TEM cell this size, the general rule of thumb would be emissions above about 40 dB microvolts are really areas of interest or concern for our ongoing testing. So we can do this setup in any kind of a room with our spectrum analyzer where we can start to see emissions in a radiated sense to validate. So we mentioned how this TEM cell setup allows us to make more repeatable measurements. So what that means is we can now take that setup and compare different board versions, different updates to get relative measurements, looking for improvement over time or looking for changes in the radiated emissions that occur. So let's take a quick look at a video that shows us how to use archived or live measurements to show this comparison, this improvement over time with a TEM cell and with our spectrum analyzer. So here we're looking at our spectrum analyzer set up for a comparison test with our TEM cell, with particular interest at the 375 megahertz values. As we start a new test, we can compare one version to the other. We see overall very similar emissions between the two types of these boards, but as we stop it, we can see that our three measurements on the side there are considerably lower than they were when we started. So we've done a good job of getting rid of this 375 megahertz harmonic within this board change. So that was a good look at radiated emissions for validation testing purposes. Now let's look at a setup we can use for validating some basic conducted emissions. Here we're going to use a LISN, a line impedance stabilization network, as part of our test setup. This really goes between the board and the power. This allows us to capture any emissions that are being conducted back into the power line. For this test, this is a DC board, so we're going to use a DC LISN that operates really between whatever the switching power supply is and the board itself. Just look at emissions that are being conducted back into the DC line. These kind of emissions can often end up being radiated emissions problems, as the cabling, the DC cabling, can act as an antenna in a final compliance test. We're also going to use some EMI software capabilities like the EMI detectors, bandwidths. We're going to start to use correction tables and limit lines on tests like this as well. This test, you're going to be able to archive the data to our system to make sure we can long-term continue to do proper validation testing on different versions. Let's go ahead and look at a video. So here we can see our test board in the front left with our DC power. Ultimately, that power in this case is coming from our DP800 linear power supply, going through the LISN, and the emissions being sent back by the board under test are being routed to the spectrum analyzer. Now we can look at the spectrum analyzer. So here we have a basic test set up from 150 kilohertz to 30 megahertz, our conducted emissions band. We've got a limit line set up that we think is appropriate for this test, and a margin set to that to give us room for improvement. We've done a background test with the device off to see what background noise is available. Now we can go ahead and run our test. So with the device on, we see a number of peaks across the conducted band. Right? We can identify peaks, and what's great about this is even though we did a peak test using a peak detector, now on the right we can see both the peak, the quasi-peak, and the CISPR average detector, and how they look at that peak frequency that's of interest to us. Another technique we can use for validation purposes, we started to see in the last video. We can talk about limit line comparisons. So not only can you use limit lines to compare to known standards across different types of products and different situations you might encounter. The RSA EMI software itself contains more than 300 different standard limit lines. But you can also use a combination of limit lines, margins, and other techniques to really optimize those limits for your own test considerations, especially in a validation setup here where we're not really a full compliance test. We might need to offset those to give us more room to be confident in our final compliance testing. So let's see how that editing and changing of a limit line process works in the RSA 3000. Here let's look at the spectrum analyzer with three different traces on the screen. We can edit each limit line individually. Here we have a limit line tied to trace 1 where we can individually modify points, or in this case add a margin to it. Right? So we can configure each one with the instrument itself, and then we can go ahead and run a quick search for validating the traces against the limit line in particular. So that allows us to see different peaks of interest and different points. We can also use our TEM cell setup as a validation test for immunity emissions as well. In a pre-compliance mode, we like to think of immunity as a functional test. So we can use it nearly from validation to debug. Here, we're looking at how the product performs when surrounded by emissions of another cause, right? So it's a susceptibility or immunity type testing. And we can do this in the TEM cell with a slightly different test setup. Here we're going to use an RF source, the modulating AM modulated RF source, like our DSG-815. And then we use a scope or another device to test functional performance of the board itself. Let's take a look at a video. So here we have our signal source connected to our TEM cell. The device in our TEM cell is connected to our oscilloscope, where we're going to monitor the digital traffic. Here, looking at our scope, as we start to turn up the signal source, we can start to see the 125 megahertz amplitude modulation starting to affect the clock signals being shown on our scope coming through the device. Here we can see that modulation starting to impact our signals, and really at a maximum of about 20 dBm, that's equivalent to approximately 22 volts per meter on this geometry of a TEM cell. So that was all about radiated immunity testing with a TEM cell. Let's look at a slightly different approach where we can now look at some conducted immunity. So this would be, by conducted immunity, we're talking about RF power coming in through the power line and how that affects the performance of our board. So this is, again, a sort of validation or a debug test where we're going to use a scope on this same product. Let's go ahead and take a look at how we set up this test. So here we have our DC listen again, connected to our power supply. We're powering this board. Here, instead of looking at the RF coming out of it, we're injecting RF power with our signal source. And this allows us to see how the device or the board is affected by that power coming in on its power line. Let's go ahead and look at the scope. Here, as we start to turn the power up, we start to see some effect on modulation on our signals there. Not as much as from the radiated high power emissions, but still seeing some changes that could affect operation. So this is a great validation check to see where you are in terms of conducted immunity testing. So that really completes our look at what we'll call validation testing, in that middle range between when you're first designing new features into a product and ultimately in a debugging mode. Now we're going to look more closely at debugging. So as we've built and designed and found some issues we need to work with in our product, how are we going to debug issues that are really related primarily to emissions, whether they be radiated, conducted, or immunity? Well, there are a couple different setup challenges and then debug challenges we want to look at. In general, I find it easiest to set up your debug tests in the same way where you originally found the problem, whether that was in a validation mode or just a visualization. Next, we're going to show some advanced capabilities here where we use real-time mode in our spectrum analyzer to time correlate these events. This is going to allow us to look at how our product is operating at the time of the emissions occur. It gives us the best chance to go back and debug and solve problems quickly and efficiently. Let's take a look at some of these setups, capabilities, and techniques. The first debugging technique we're going to look at is a type of power emulation. So here we're looking at conducted emissions on our DC powered device. And one good example of basic debugging here is first we're going to look at the conducted emissions with our device and our switching power supply. And we're going to compare that to how it works with a linear power supply like the DP800. Then we can go back and use a listen to really check the actual conducted emissions output of the switching power supply. Those two tests help us isolate different components. They're going to help us find the root cause of our debug challenge. Let's take a look at the video. So here we have our RF current probe around the DC line. And here what we've done is we've connected this to our standard switching power supply. We can see a couple peaks here in the conducted range. let's try to isolate these signals. So here, let's go ahead and switch over to our other power supply. So now we're going to switch on to our DC linear power supply and look at the differential. So here, using the real-time spectrum analyzer, we can see, significantly less conducted emissions at particular frequencies of interest here, especially like that peak. Now, testing this another way. Here, we've got our switching power supply, where we're loading it with an electronic load through a listen. So what this does is it draws the power out of the switching power supply and allows us to monitor the conducted emissions being generated in this direction on the spectrum analyzer. This is another way to look at the power and the conducted emissions being generated by a switching power supply. In this case, when we go over to the spectrum analyzer, what we see is, well, obviously we have a limit line set up and a margin and our background test. And here you can see that's a peak. Now, if we go ahead and run that test, we see a very different looking sort of emissions set from our conducted emission. You can see on the DC side, near DC side, we have some relatively high emissions coming out of this switching power supply, up near 60 dB microvolts. And then as we get higher, right around 10.5 megahertz is the main peak at number 1 there. That's the switching frequency of the switching power supply. So we can see what emissions are being caused there. So this is another way to look at how much power is coming off of our switching power supply, both with a load and emulating it with a power supply. So a great kind of two-phase test to isolate any conducted emissions related to a switching power supply. So the next debugging step we want to look at is really about real-time debugging. Here, using the real-time analysis capabilities, the real-time spectrum analyzers, what we're going to be able to do is look more closely at how those emissions are changing over time. So this is a great way to find short-term emissions or transient emissions that might cause you a problem ultimately in a compliance test, but aren't easy to see in a traditional swept spectrum analyzer. We're also going to use the spectrogram view to give us a feeling of how those things are, how those emissions are moving over time. That can help us, again, isolate and identify ultimately the root cause. Let's take a look at a video. So here, for this radiated debugging test, we're going to use the near-field probe close on our device to look at some subtle effects and changes. Now let's look at the spectrum analyzer. Here we're focused on the 40 megahertz band, right around 875 megahertz. That's the 7th clock harmonic. We're going to use the spectrogram display. This allows us to see the waterfall chart, or really the changes over time. We can see some subtle effects here as this chip that we're focused on really has a reset and then has some frequencies that move around in this span that are frustrating us. We take a closer look, we can see right there a reset occurs and the power drops across this whole spectrum. Now over the next 30 seconds it builds again and resets, and this is a continuing, reviewing, kind of renewing cycle. If that was annoying us from a pre-compliance standpoint or from a functional standpoint, we could use this kind of real-time test with super accurate RF measurements to isolate the ultimate cause of that, what's causing that dithering frequency and that power building, and do something about it. So we looked at some conducted and radiated emissions debugging techniques using both power and then our real-time mode. For more complete debugging, we can use some time-correlated debugging. Using a spectrum analyzer and an oscilloscope together, with the right configuration, we can see both the real-time RF and analog and logic channels of our board as well. By being able to view these events together, we can then really quickly settle in on the root cause of any of the particular RF emissions that might be causing us trouble. So here again, we're going to use the spectrum analyzer to capture the RF. We're going to use the IF output from that spectrum analyzer to connect to the oscilloscope, and some triggering between the instruments to really allow the oscilloscope to capture and trigger on both RF, digital, and analog signals all at once. Let's take a look at a video. On the right, you see our spectrum analyzer, where we're occasionally catching a pulse emission. Left is a scope. Zooming in on the scope, you can see we're using that RF trigger. We're seeing that RF pulse in the middle. We're triggering now using that frequency mask you see there. Back to the scope, you can see how the logic channels we can now see are coordinated with the RF pulse activity. So we can find the root cause in the digital channels. So now we've looked at all of our visualization, validation, and debug tests across radiated, conducted, and immunity compliance measurements. So that really shows you now that we can debug everything from simple radiated emissions using a power supply and looking at the cause and effect of a switching power supply conducted noise, to our radiated emissions, and really finally to using the full capabilities of real-time mode to look at time correlated debugging that we can do with both a scope and a spectrum analyzer together. Really at the heart of our EMI PreCompliance Solutions is the new real-time spectrum analyzers here at RIGOL. Models like the RSA 3000 really allow you to do both swept analysis with high performance for visualization tasks, real-time mode, which is great for some validation and a lot of debugging tasks like we just did, and then our new EMI mode, which is really ideal for your radiated and conducted validation tests with over 300 limit lines preset, pre-built into the library. It also enables your EMI average, CISPR average, and quasi-peak detectors that you can use for a number of pre-standard pre-compliance setups. With test report management and test data management, you're really able to archive all of your data, compare traces, and compare limit lines to get as close as you need to for confidence that you'll eventually be able to pass a full compliance test. One of the other great things about the RSA 3000 instrument is it allows you to use seamlessly in a number of ways. You can use it as a traditional instrument with the knobs and buttons. You have a full touchscreen control, and it can also be used with a keyboard, a mouse, and a monitor, which is a great use if you have a more elaborate test setup or a chamber where you need to be isolated from the spectrum analyzer. Let's go look at some of the other accessories we need when doing these kind of EMI pre-compliance measurements. So there are some additional accessories we use throughout these tests that can help us at different levels between visualizing, validating, and debugging our pre-compliance signals. Some of them, like the TEM cell and the listens from our friends at TechBox. Others, like the near-field probes, attenuators, other accessories that we have here at RIGOL. Additionally, we used a number of different instruments, including our oscilloscope for functional tests. We used a linear power supply, DP800 series, to handle many of our power emulation modes. We used a DSG800 signal generator to put out our susceptibility signals for immunity testing. And we also used electronic load, DL3000 series electronic load, to draw power out of our switching power supply when we were testing its conducted emissions. So overall, there are a number of different probes, setups, and connections that you need depending upon where you are in the design cycle and what type of emissions you're trying to test. As you continue learning about EMI pre-compliance measurements and how you can utilize them for best results within your design cycle, RIGOL has a number of online resources that we think can be helpful. You can find many of them linked to or at our rigolna.com/EMC page. From there, you can get to our step-by-step TEM cell emissions test guide, which is a great look at kind of each step in a radiated emissions validation test setup. We also have our RF Basics Technology Guide and our Pre-Compliance Primer. These documents are great summaries of many of the topics we've talked about today and how we can use different instrument capabilities in visualization mode, validation, and ultimately debugging to get the most out of all of our EMI pre-compliance test setups. So today we've looked at how we can use pre-compliance measurements throughout our design cycle to save us time and money when we get to real compliance testing. We can visualize tests during our implementation phase. We can validate emission signals during our test phase. And when needed, we can debug using real-time analysis and time correlated data to really find root cause problems of any emissions that might be occurring. Using RIGOL's real-time spectrum analyzers that combine all the modes necessary for these EMI measurements, including swept mode, real-time, EMI application mode, as well as advanced triggering, we're able to provide a test bed for complete EMI pre-compliance measurements throughout all phases of your design cycle, all in one instrument. With additional capabilities and accessories, you can get a complete test setup that is both affordable and valuable for your EMI pre-compliance measurements.